All right, guys, let me start it up. Okay, you guys, so today's lesson is essentially about what's called Hess's Law. Before we look at that, it says, well, why does his beer cost less than mine? She says it's the senior discount. The senior discount. Is that right? You guys think that was fun? Not the senior discount, but the senior discount. Anyways, delta H is, you guys remember delta H, remember that's a change in. H is enthalpy, another word for potential energy. You guys remember all matter has energy, and so when their chemical change occurs, matter changes from one form to another, you're going to have a change in enthalpy. It's saying we can estimate delta H using published delta H values and the properties of enthalpy. You're like, what the heck does that mean? That's what we're going to be looking at here. So, for example, let's say we've got a reaction. You guys, here's a pretty common reaction. We got methane. You guys remember that's the gas we have in our Bunsen burners, and that is combustible. It reacts with oxygen. Whenever you have a hydrocarbon and oxygen react, you're typically going to form carbon dioxide and water. And so look, as we go from these reactants to these products, it has a delta H of negative 890 kilojoules. And you guys remember when delta H is negative, that means heat is released, heat is lost. That shouldn't be surprising. That's why when we use the combustion of methane to generate heat. 890 kilojoules of heat is released. Okay. What Hess's law is saying is we could look at this overall reaction in any number of individual steps. You might look at the reaction as first happening, like look at, let's say the original reactants form this first, and what this is showing is they're saying maybe one of the carbons combines with one of the oxygens and forms carbon monoxide, and then two of the hydrogens combine with one of the oxygens to form water, and then we still have some oxygen left. And then this would, and then for that reaction to occur, if that were to occur, the delta H for that would be negative 607 kilojoules. 607 kilojoules of heat is given off when it goes from this to this. And then this could proceed to continue to react in such a way that the oxygen here can combine with the CO here and form the carbon dioxide, and then we obviously have water. So then that process, let's say from here to here, has a delta H of negative 283. But what do you guys notice? If we were to take this delta H value and add to this delta H value, right? Because this is, you could say the overall reaction is the sum of these two individual reactions. What do you guys notice about these two values? When you guys get the exact same value here. So that's what Hess's law is indicating. Really, the only thing we need to know is the delta H is determined by the enthalpy of our original reactants and our final products, regardless of the number of steps it took to get from our original state to our new state. It says, and this is in purple, guys, so you probably write that down. Delta H for the overall reaction will be equal to the sum of the enthalpy changes of the individual steps. Like I said, we add this to this, and you're going to get the overall delta H. Here's a new concept for you guys. Notice it says delta H, and then it has a little f. That is for formation. That's the enthalpy. That's called enthalpy of formation. I probably should have purpleized that. It says that that's when a compound is made from its constituent elements in their elemental forms. So, you guys, every compound has what's called an enthalpy of formation. So, I don't know, I'm going to look, see if you guys can see these. I don't know, I know they look kind of small, but you guys will see various substances. I'll just point to some, like methane, CH4 has an enthalpy of formation of negative 74.80. Let's look at another one. Carbon dioxide, where's carbon dioxide? That's a common one. Carbon dioxide here, CO2, negative 393.5. And notice that the units is kilojoules per mole. So what we mean by enthalpy of formation? So carbon dioxide has an enthalpy of formation of negative 393.5 kilojoules per mole. What that means is, you guys think about it. When carbon dioxide was formed, what would carbon dioxide be formed from? When you guys agree? Isn't it formed from carbon and oxygen? So when carbon combines with oxygen to form carbon dioxide, that is an exothermic reaction as indicated by the negative delta H of enthalpy of formation. So what we're saying here is, for every 1 mole of carbon dioxide that's formed from carbon and oxygen, 393.5 kilojoules of heat is given off from that reaction. That's called an enthalpy of formation. In a sense, it shows you pretty much how much energy does that substance have. So for example, and if we were to go the reverse direction. Let's say we go carbon dioxide. Let's say so this is the synthesis of carbon dioxide. Let's say we were to go the decomposition. So if we were to take carbon dioxide and break it down into carbon oxygen, you know what you would do? You would just reverse this. There's still 393.5 kilojoules of energy involved, but if you go the reverse way, what happens to the sign? It becomes positive. That means it would require 393.5 kilojoules of energy in order to decompose carbon dioxide back into carbon and oxygen. Okay, so that's the enthalpy of formation, is how much heat is given off or was required to form the compound from its constituent elements. One thing you guys will see on here, notice you will not see any pure elements. You guys, by definition, the enthalpy of formation of a pure element is going to be 0. And why 0? Because the thought is, well, the element has always been that element. There wasn't any heat given off or required in the production of that element that has always existed. So it's only for compounds. All right. We'll show you guys how you can use those enthalpies of formation to calculate some values that you might need. So let's say we have this reaction. Here's C3H8. Once again, that's another hydrocarbon. That's actually propane, what you guys would have in a white tank, right? You might go camping with or whatever. Propane, it's combustible. And once again, in typical fashion, what did I say? Hydrocarbons are combust to form carbon dioxide and water. It's always, it's got a lot of the same things. Okay, so let's say we had to calculate the delta H for that reaction. Here's one way you could do it. You could look at this reaction as a series of sub-reactions. I could look at it as, for example, let's say I look at propane breaking down to its constituent elements. You guys see that? So I could get a delta H associated with that. What would I do? I could just go back to my enthalpy of formation for propane. I'm going to look for propane. Propane, the enthalpy of formation reads negative 103.85. Remember, that's saying it's negative 103.85 if we were producing propane. But look at how we're writing it. We're showing propane being decomposed. So what do we take that? We take that negative 103 and we just reverse the sign. So in its decomposition, it would require 103.85 kilojoules. Okay, so we're showing that. Then we can also look at, let's look at the production of carbon dioxide. Once again, if I wanted to show the production of carbon dioxide, I could, you guys see it. Then we could say in this reaction, when the propane breaks down into carbon and hydrogen, then one of the carbons reacts with oxygen to form carbon dioxide. Well, how could I get that value? Once again, I would look back on my enthalpy of formation, look for carbon dioxide. In that case, the one for carbon dioxide, if I'm looking, here, we'll just go back. So, carbon dioxide was negative 393.5. Okay, so, but remember, looking back here, that's kilojoules per mole, but look at how we're writing it here. We're showing the production of 3 moles of carbon dioxide, so I just take that value and I multiply it by 3, okay? And then I would get this value here, negative 1,181. And then I could say, okay, then what happens is, from our original reaction, right, when I produced hydrogen here, the hydrogen is going to combine with the oxygen and then form the water, okay? And now look at the sum of these, and then I could get the delta H for this reaction by just getting the enthalpy of formation for water, remember on the previous chart, but then I'd multiply it by 4, because remember that was per 1 mole, we're showing the production of 4 moles. Now look at the sum of these reactions. Check this out. Guys, look. So I could just sum up these reactions, right? So look, if I produce 3 carbons and then 3 carbons is used up, can I cancel those out? Like just imagine you're just adding these all up, okay? And then I produce 4 hydrogens here, but then I'm using up 4 hydrogens here, so I take that out. And then I have propane, and then look, I've got, on the reactant side, I have 3 oxygens and 2 oxygens. Wouldn't that be 5 oxygens? Check it out. And then I have 3 carbon dioxides and 4 waters. And what do you guys notice? We end up with our original reaction. So let's say I had to determine what is the delta H for this reaction. I want to know, hopefully, there's one thing you guys can predict. There's something you should be able to predict about the value for delta H here before you do any calculations. It better be a what kind of number? It better be a negative value. You know why? Because this is a combustion reaction. You know heat's given off, okay? So it better be a negative value. So how can I do that? Well, since these are since this is a sum, these sub-reactions sum up to the original reaction, I can just get the delta H of all those and then add them up and get my delta H for the reaction. So that's one way you could calculate the delta H for a reaction, is adding taking the sum of sub-reactions whose addition makes up the original reaction. Once again, that's what Hess figured out, It doesn't matter how you go from the original reactants to the original products. All that matters is ultimately you go from the start and you end up at the final products. Okay, you guys, there's another thing we could do. Okay, you guys write this down. This is purple. I know it looks kind of complicated, but basically this is saying delta H, right? We're just talking about delta H. You could look at it's really the change in enthalpy, or you could look at it. They sometimes call it the heat of reaction because right, energy is usually in the form of heat when we're calculating it. This is the sum value, and then the N is the number of moles, and then so this is saying that the enthalpy of formation of the products. Essentially, you guys, you know what you guys could put if you guys wanted to just make this a lot easier. Delta H is you just get the enthalpy of formation of your products minus the enthalpy of formation of your reactants. And you guys, that's typical fashion. You guys remember what I was saying with delta? That's a change in, and whenever you get a change in by convention, we always do final minus initial. We take the enthalpy of the products, which is our final, minus the enthalpy of our reactants, which was our initial. So let's show you guys how you would do that. So once again, this whole thing is just different kind of variations of how to ultimately calculate the delta H of a reaction. That's a very important thing that chemists would want to do. We'd want to know how much energy is associated with a certain type of chemical reaction. So we can do the same thing. I'm just showing you a slightly different way. Remember we just showed it as a series of sub-reactions, kind of breaking up the original reaction into different types of reactions and then adding those together. Or you could just do it, the sum of the products minus the sum of the reactants. So delta H, I take my products. You guys see, we start with our product side. Remember, it's products minus reactants. I would take the enthalpy of formation of carbon dioxide. And where would I find that? You'd find that on a table. You remember the table we saw a few slides back? The enthalpy of formation for carbon dioxide is negative 393.5 kilojoules. So I put that. But then you guys got to remember what do you need to do to it. Remember, this is kilojoules per mole, so you have to multiply by 3. So I take that, multiply by 3. Then I would add that to the enthalpy of formation of water, which is negative 285.8. Well, then what do I have to do to that value? You'd have to multiply it by 4. Okay, let me just show you. I don't know if you guys can see it. So that's what we're showing, before I do that. Then, well, yeah. So that's what I did here, right? 3 times that, and then 4 times that. Then you do minus. Remember, it's the products minus the reactants. I do minus. Then I do the enthalpy of formation of now my reactants. Propane, the enthalpy of formation is negative 103.85. I don't have to multiply that by really anything because it has a coefficient of 1. And then you notice, look, it says plus. But they're taking into account the oxygen. Oxygen is really easy, guys. What's the enthalpy of formation? You notice somebody will be like, well, Miss Wilson, where's the enthalpy of formation of oxygen? If you guys remember from a few minutes before, I said oxygen is a pure element. There's no enthalpy of formation because it's always existed from a physical standpoint. Therefore, it is just 0. So now it's just a matter of doing a correct calculation into our calculator, and we punch it in, and we would get ultimately the value negative 2,219.9. Once again, it's negative. That helps. That should give us a little bit of certainty that okay, perhaps we're doing it right because it's a negative value indicating heat was lost. And then you'll see that is the same value we would have got using the other technique by adding up the individual sub-reactions. Okay, several ways to ultimately calculate, guys. This is really big, calculating a delta H. Says, these are not the speeders you're looking for. He says, cool it with the Jedi mind tricks. He's trying to pull one over on that cow. Okay, you guys, delta H, here's why it's important. You guys, right? We talked about it, right? Food. You guys know what food is? Food is just, you guys remember, all matter has energy. Food is just the type of matter that has energy that you and I can immediately access via digestion and cellular respiration to utilize the energy associated with it. That's all food is, as far as a category of matter. And you guys, right? And how do we measure the amount of energy that food might have? We do so with calories, right? That's what you guys are familiar with. And so we would take a food item, we would break it down, basically you'd blow it up. You can imagine heat would be given off. We can use the technique that we talked about last video lesson to using a calorimeter. We can measure how much heat was absorbed by the calorimeter, and thus, if assuming no heat loss, we can assume that that's the amount of heat or energy associated with that food item, and that's how we ultimately determine how many calories a food item has. So you guys, I want you guys to look at several different items here. Don't worry about carbohydrate, fat, protein so far, but look at here. And you guys look, which food item has the most calories? Which food item has the most calories? And if you guys look, you should see the one that has the most calories. You guys should be looking, if you guys are going to do a comparison, you know, it's going to be kilojoules per gram or kcals per gram, however one. But either way, you guys are going to see it is this one right here, and it is cheese. Cheese. Of all these, assuming we had, right, it says per gram, so we're comparing like amounts. It's actually cheese. So the question I might have, why do you guys think cheese would be so energy dense? Well, if you guys think about it, you got to think about what it's made up of. You guys, all your food items are made up of potentially three different categories: carbohydrates, fats, and proteins. And you think about, what is cheese? What does cheese have a lot of, guys? It does have some protein, but it's primarily what, guys? It's primarily fat. Now you guys look, compare carbohydrates, fats, and proteins. If we took a gram of each, if you take a gram of carbohydrate and you want to break it down, it's going to require 4 calories of heat to break that down. If you want to break down a gram of protein, it's going to take 4 calories, food calories of energy. But look at fat. Fat takes a full 9 calories. So you guys, it's a lot more, so things that contain fat, that's why when people are on diets, they'll tend to try to reduce their fat intake, because fat is a lot more energy dense than proteins or carbohydrates. One last thing, guys, in light of delta H, really important. Think about, these are different fuel sources, right? You'll notice they're all combustible: wood, charcoal, oil, gasoline, natural gas, hydrogen. So just looking at that, and then they kind of, you guys see they're all pretty much hydrocarbons, and some have oxygens in them. You guys, a lot of organic compounds, or carbons, hydrogens, oxygens. Of all those guys, which is the most is the most energy dense? Basically, when this combusts, you're going to get the most energy from it. You guys look at the chart, and you guys should notice, you know what, this should be easy because they're actually in order of energy density, and you'll see it's actually hydrogen. You guys compare that. You guys compare that to gasoline, which we use to run our cars, right? Gasoline has 48 kilojoules per gram of gasoline. Hydrogen, when you burn that, 142. It's like 3 times as much. 3 times as much energy per gram using hydrogen as you would gasoline. And you guys, that explains why there's a lot of people trying to figure out how we can use hydrogen fuel cell cars to run our cars, because then it can even be more energy efficient than our current gasoline powered combustion engines. All right, guys, good stuff. Glad you guys could join me. Until next time, bye.